Okay, we didn't plan it, but we somehow have Professor Babak Hassibi, also from Caltech, giving the talk right now. So we are very happy to have you over here. And Babak also has a very strong body of work, and we will see that in many of the talks, at least in my talk later today, we are going to refer to your work as well. Yeah, so it's really great to have you over here, and you have the job of following up.
Thank you. Yeah, thank you, Arya. Thank you for the invitation. Thank you all for realizing I'm the barrier between you and lunch. I don't really know how to follow John's talk, so I thought maybe before I start my own, I should contribute a little bit to his. He talked about, crazy pictures of everything connected. So I looked on the internet and I found this. So I think this is an example. This is New York in 1890. And it says, multiple electric lines were required for each class of device. So lights needed a voltage. I don't know, the grandfather clock needed a voltage. And so Tesla came along and said, hey, you could do AC and you could use transformers. And so now we have 110 volts. And each device has its own transformer. And if you know, Edison hated AC. He didn't like Tesla too. But the reason why he hated AC is because you had to use complex numbers to understand AC. And Edison did not know what a complex number was, so he dismissed it. Anyway.
You still use DC at the periphery.
You do use, but I mean.
So you now mix them, right? Yeah.
You do mix them, but anyway, I mean, you could not have had the power system without AC at least. Maybe now you can, but back then certainly.
Right, absolutely. Perfect example.
Anyway. So that's a picture. Let me get to the business of my own talk. So hopefully that's anyway. So I want to talk about something a bit more related to optimization, which I guess is the theme of this. And so control is kind of I mean, I'll be talking about optimal control. So it is optimization. It's decision making. It's, as you'll see, it's online, and it has to look into the future. And so I want to talk about, something I'm quite excited about this. It's a new way of looking at stochastic optimal control problems. I'm calling it linear Bregman divergence control. That'll become clear pretty soon. This is joint work with two of my students, Judy and Reza. And it's very recent work. So, some of this is just being submitted, or was submitted to CDC. So here's the outline. I'll talk about the control problem, but I want to talk about using non-quadratic convex costs in control. May not sound too controversial, but I'll show what some of the issues are if you truly want to do control with non-quadratic costs. I'll introduce Bregman divergence, what it means. Many of you might have seen it, what it could do for control, and then I'll give examples and conclude. Okay, so the motivation is this, I mean, if you worked in statistics or signal processing or machine learning, anything, the last few decades, the use of non-quadratic, non-smooth convex costs has kind of become ubiquitous. It's revolutionized, I would say, these fields. Up until maybe 80s, 90s, everything was kind of least squares, and you had SVDs and this kind of stuff. But compressed sensing, L1, low rank matrix recovery, Mariam is here, nuclear norm minimization, cross entropy loss. These are all convex losses that we use, but they're not quadratic. And so they allow us to, get solutions that are very different, sparse solutions, low rank solutions. We can structure the kind of solutions we want. But if you look at control, by and large, people use quadratic costs. The traditional control problem, LQG, you have a quadratic cost on your state, a quadratic cost on your control. There's some randomness in your system, say, and you kind of take an expectation of this cost. John talked about robustness, and so this is kind of a cartoon of an H infinity problem. You look at your disturbance in worst case, but again, everything is looked at quadratically. Again, you have a quadratic cost in the numerator that you want to keep small, and you penalize quadratically your disturbance. And so the question is, why is there this fixation on quadratics? And so let me kind of motivate this. So I'm going to do a little bit of math. There's no getting around it. So I'm going to focus on a simple linear state space model, which is time invariant. So X is the state, U is the control, A determines, how the state evolves, and B relates the control to the state. And so the simplest problem you can think of is what's called the linear quadratic problem, which is so this is a noiseless system. I'll get to noise in a second. You have a quadratic cost on your state, a quadratic cost on your control, and you want to choose the control signal that minimizes this. This looks very straightforward. You can solve it. I won't do it here. And, you could say, well, what's the big deal about, putting, non-quadratic convex things here? I can put my favorite convex cost on the state, my favorite convex cost on the control. Okay, this is a convex optimization subject to the equations that show how the state evolves. And I can solve this, right? I mean, in principle, I can solve it. It's not a big deal. So for example, I might say that, hey, why not put an L1 cost on the state? So the only difference with the LQR is I replace the quadratic with 1. I can solve this problem. This is a boring figure, but I'll show it nonetheless. So the blue here, so what I'm showing you here is that this is a particular system. The detail doesn't matter. This is, say, the magnitude of the state, 2 norm of the state, if you will, as a function of time after you apply the optimal control. The blue is the LQR solution. It gives you a linear controller, and so you kind of decay to 0 at the boring exponential rate. The L1 controller, because it wants to sparsify the state, smack takes you to 0 at a particular point. So in finite time, it gets you to 0. So it behaves quite differently. It allows you to get the state, to 0 much quicker. If I put more of a penalty on the L1, I can actually shift this earlier. It will take the state to 0. It will pay some price early on, but it will push the state to 0 much earlier. So you can get, different type of behavior. I can do other things. I can look now maybe at the cost.
Babak,
Yes.
you pay a big control cost for that?
You will, yes. I mean,
Okay.
again,
There's a trade-off.
there is a trade-off. Yes.
Yeah.
There is a trade-off, and you'll see it a lot. I'll get to much more
Yeah, okay.
involved examples.
Because I just think, I think one of the real, that's a space of trade-offs. It's very.
Yes.
Very.
Right. And so here I just want to show another one. So let's now put a peak constraint on the control, to your point. So I'm saying, you're not allowed to use a control bigger than delta. I'm keeping the L1. And again, this is just a simple convex optimization problem, which I can do. And so here I've shown both the control and the state. So the red is the LQR controller. Behaves this way. This had a peak value on U, which I guess we took to be 20 here. So it kind of restricts so that the control cannot be as aggressive in the beginning as the LQR. As a result, it pays a bit of a price beginning. The state is not behaving as well as the LQR, but because I was putting an L1 cost on the state, after 5 steps, it did push it. Whereas the red one is going exponential. Okay, so this shows some of that. Because we had put a penalty on a peak penalty on the control, the behavior at the beginning was bad, but it did push it. Absolutely to 0. Okay, so the only thing I want to draw from this is we can get exotic controllers through choices of these costs on the state and on the control. And so why am I giving a talk? We can just do this, right? So there's 2 issues that come up, which is why I'm giving a talk. First of all, the optimization problem, if you're solving it over horizon T, the complexity grows with T. It's a big optimization problem. And so maybe you don't want that. And as you let t grow to infinity, I don't know how to get stability guarantees or anything like that from this. But the more important question, and what I want to focus on, is that the state evolution, the systems typically have some kind of uncertainty. In this talk, I'll assume they're random. There's some kind of randomness here. And so as soon as there's randomness here, we can't really do what we did earlier. We don't have a deterministic optimization anymore. Okay. So when there is randomness, what you have to do is you have to look at the expected cost. Again, if we're living in the stochastic framework, there's other ways to look at it too, for another talk maybe. So we're going to look at the expected cost. And as soon as we talk about something random, it's important to identify what information is available to the control. Okay? In the deterministic case, that was not an issue because there was no uncertainty about what's going to happen in the future. You just solve an optimization problem. Here, it does matter what you know about the system. And so the information available is critical. And in this talk, for simplicity, I'll assume the information available at time I to the controller is the current and past states. Okay, so it's called full information. There are other cases I can look at too, but for this talk, I'm going to restrict myself. So the controller can be a function of current and past states. It's not clairvoyant. It cannot see the future. And so we're looking for an optimal policy now, which is how we choose to use as a function of states. And I would like to solve this problem. Okay, so I want to put arbitrary convex costs here. I'm interested in the expected value. This expectation is over the randomness and subject to this constraint. Okay. So if I, write these xi's in terms of b's and u's, there's randomness in the arguments here. And so I'm looking at expectation. Okay. So it's a more complicated problem. And so first, I want to look at it a little bit because I want to show you what the difficulty is and then what we get around to actually trying to solve it. So I'm going to take, throughout this talk, this is a simple scalar system because it will reveal all the important things without having us getting bogged down in complicated formulas. Okay, so it's a one-dimensional state. Little a is a scalar, little b is a scalar, everything is a scalar. And I'm going to assume that the noise is standard normal, white. And so let me take a special case where Q is an absolute value and R is a quadratic. So I'm putting kind of like an absolute value or an L1 norm on the state, but the penalty on the control is still quadratic. Okay. And so the way people solve this is by dynamic programming. So you start at the very end. If you look at this, expression here, I'm minimizing over all these u's, but u at the final time, u at time capital T, only influences x at time t plus 1. So the minimization over ut I can do first because it's the very last. Yes.
Just a question. Do we know if separation principle still holds when the cost is not quadratic?
I will talk about that.
Oh, okay. So
it depends, not for this, but I'll talk about that. That's a very good question. But let me just show you what the difficulty here is. So I'm looking at the last step. So if I want to find ut, so the control at the last step, this is the problem I have to solve. Because ut does not influence any of the other terms in the summation. Because the future is not influencing the past. So this is the last term. And so if I want to do this optimization, the first thing I have to do is do this expectation over W. And when this is quadratic, I know how to do it. I put an absolute value here because that's the cost that I have on the state. So it turns out for the absolute value, you can compute it. It's this horrendous thing. It has a Q function, which is the tail of the Gaussian. It has an exponential. But we got rid of the W. This is now a deterministic function in X. Excuse me, in U, which is what we want to optimize over. It's deterministic, it's convex. So in principle, I can do it. And you will get some solution. I don't know what it is in closed form, which is function of it. So I can numerically solve it. My U will be some function of the current state. It's like a state feedback. I can take that and I can plug that back into this expression. And this is kind of the optimal cost, sometimes called the value function. It's the cost to go. So if I did the optimal choice at time t, this is the rest of the cost. Okay. And so now if I move to the next time step, okay, ut minus 1 is what I have to choose. So ut minus 1 appears in the cost at time t minus 1 for these two terms, but it also influences the cost to go. So I have to bring the cost to go, replace xt with xt minus 1 and ut minus 1 and bring it in the cost. So the next step is what I have to solve. The cost to go always comes back, this is dynamic. Okay, so this is the difficulty. I need to do the expectation here, but I don't even know how to evaluate this. I can compute it, but I need to take its expectation over W. And so the only way I can do this is by Monte Carlo, which means that I have to generate random W's. I have to solve an optimization problem for that W to compute this. And I have to do enough of them so I get an estimate of the expectation of this. And then after that, I have to do an optimization for ut minus 1. It's very complicated. And if you try to do an extra step of this, you'll need two set of nested Monte Carlos, one for MT, one for MT minus 1. So it quickly blows up in your face. And so nobody does this. Sometimes they do it, with looking 2 steps into the future, because maybe that they can afford to do that, but you cannot do the full shebang. Okay, so these are sometimes called receding horizon control. So where you're not greedy, you don't make a decision based on what's best for you now. You try to look, maybe 1, 2 steps into the future. And as you move forward, this horizon moves. But ideally, what you want to do is to look at the whole horizon, which is not doable. Okay. So I want to be able to solve that problem. And so to attempt to do that, let me show you why things work in the quadratic case. Okay. So in the quadratic case, again, if you look at time t, the very end, you have a quadratic cost on the control, a quadratic cost on the state. There's randomness in W, and I have to take the expectation. But because this is a quadratic, the expectation is very easy. If you expand out this quadratic, it'll have a term that's quadratic in what's known at time t, which is this term. It'll have a quadratic term in W, which has some expectation. The important thing is that there's a cross term, which goes to 0 because W is 0. Okay. And so this is independent of U. And so you're left with a simple deterministic quadratic. The expectation is easy to do, and you're left with a very simple quadratic optimization, which you do. The solution is the famous linear feedback wall. You can explicitly compute the cost to go. The expressions are hairy, but can be done. And then you can take this cost to go, add it to what you have at time t minus 1, that brings up this extra thing that's there. The details not important. Again, what's important is this again quadratic. When we replace xt in terms of ut minus 1, you can do the expectation and you get the famous Riccati recursions. I won't go into that. But the point is that everything stays quadratic. So there's 2 things that make the quadratic case work. The expectation can be done in closed form, so I don't have to Monte Carlo anything. And the deterministic minimization that you're left with also has closed form because everything's. So it looks like this is very happy coincidence, and it certainly won't happen for arbitrary convex. And so if you look at the infinite horizon case, which is what I want to focus on, it's the most interesting one. So you're looking infinitely. This is kind of the cost that you want to look at. So I look at the average cost up to time t, the expectation, and then I push t to infinity. That's what I want to minimize. It's well known there's something called the Hamilton-Jacobi-Bellman equation that solves this. But again, I can write it down, but I don't know how to solve it because I have an expectation that I have to do over W, and somehow I have to find an M that solves this. It's not tractive. Okay. You can get a Lyapunov function out of this. Again, that's not important. Okay, so now that I've kind of maybe described the difficulty, so ideally what I would like to do is to somehow mimic for non-quadratic convex functions, or at least for a class of them, what we can do for quadratic, and kind of open up, you know, as John mentioned, the trade-offs that we can get between, you know, our control dimensions, kind of state behavior, beyond just the boring exponentially decaying, you know, states. Okay, so to do this, I'm going to introduce something called Bregman divergence. A lot of you might have seen this. So in Bregman divergence, we start with a convex differentiable function. Sometimes it's strictly convex. Doesn't matter a whole lot right now. So this function psi we call a potential function. So it's a convex differentiable function. And so the Bregman divergence, better described through a picture. So think of this as being your convex function psi. The Bregman divergence, it's a function of two arguments. You take the function at some point W, and you subtract from it the first order approximation to the function around another point W prime. Okay, so at W prime, you draw this tangent, and you look at the difference. Because this is the convex function, the tangent is always below, so this is always non-negative. Okay, so the Bregman divergence is always non-negative. Essentially, we look at W and we're removing the 0th and 1st order terms. We're left with quadratics and higher orders. That's what Bregman divergence is. As I said, it's non-negative. It's convex in the first argument, because that's convex and that's linear. Who knows what it is in the second argument, but it's convex in the first argument. And if you have strict convexity, it's 0 if and only if the two arguments match. There's lots of examples. If you take your potential to be squared Euclidean, the Bregman divergence is just the squared Euclidean distance between W and W prime. If you take psi, say, to be negative entropy, which is convex, because entropy is concave, you get KL divergence, or relative entropy. Okay, so there's lots of examples. So basically, Bregman divergence allows you to start with a convex function and then get something that kind of looks like a distance. It's not a distance, it's a divergence, but something non-negative. Okay, so why do I care about this? So Bregman divergence, because, you know, we take the convex function and we remove the 0th and 1st order terms, you're left with quadratics and higher. It shares many characteristics of quadratics. I'll show you a few. From high school trigonometry, you probably remember some law of cosines. You know, I have a triangle here, whatever. Right, this is true, right? It relates, I guess, that to the law of cosines. I'm not good in my high school trigonometry, but there's a Bregman divergence counterpart to it. More important for us, you know, again, from high school, when you solve the quadratic equation, you completed squares. There's a completion of squares for Bregman divergence too. And so a lot of quadratic optimization relies on completion of squares. So there's lots of properties that it have. For this talk, the most important is the following, right? So when we were doing expectations of our cost, okay, so let's assume I have a quadratic. Let's assume W is random, V is deterministic, and I want to take this expectation. We've all seen the trick. If you add and subtract the expected value of W, the cross term goes. You get a deterministic term, which is V minus this thing, and then you get the expectation of a random. Okay, but the point is that with this formula, you can kind of separate out. V no longer has any expectation. Right? If I had to do optimization over V later on, I can do it because the randomness is moving. There is something identical for Bregman divergence. So this is probably the most important equation in this talk. So if I'm looking at the expectation of the Bregman divergence between something deterministic and something random, I can break it up. It's kind of like inserting this expectation. So you insert the same thing here, and you put it here in the first argument, and this separates. Okay? And so the object here is not the expected value of W. Rather, it's the expected value of the gradient of the potential evaluated at W, and then going through the inverse of this gradient. So think of the gradient as being a mapping. And so that's the same object that's here. So for example, in the quadratic case, if psi is a quadratic, the gradient is linear, it's identity. And so this is just its expected value of W, and that inversion is just. Okay, so that's a special case. So why am I doing this? Okay, so this is the whole proposal in this talk. So ideally, this is what I would like to do, right? I would like to be able to solve this optimization problem where I put an arbitrary cost on my control, an arbitrary cost on my state, and minimize this expected cost. And I don't know how to do it. So I'm going to change the problem. I always tell my students, you know, when you have we're engineers, right? We're not mathematicians, right? So if you have a problem you can't solve, maybe you can move the math a little bit towards the problem, but most of the issue is moving the problem towards the math. And so I am going to do that. So I'm not going to solve this. I'm going to solve this. Okay, so I'm going to say the cost I'm going to put on the state is going to be a Bregman divergence. And it's going to be the Bregman divergence between, so if I look at this quantity here, this is x at time I plus 1. It's going to be the Bregman divergence between that part of x I plus 1 that I know when I'm sitting at time I, so this is deterministic, and the randomness that I don't. Okay, so when Q is a quadratic, this boils down to the standard LQG, because this Bregman divergence is just the 2 norm of this. So that's what I'm doing. So I'm changing the problem to, rather than make xi plus 1 small, I'm going to try to reduce the Bregman divergence between the deterministic and the random part. That's how I'm changing this problem. This I'm not doing much. This is just a facetious way of writing this. I just wrote it as a Bregman divergence because when I put a 0 in the second argument, it recovers the cost. So I'm going to assume that these two functions are non-negative, convex, even potential. Sure. And their minima are at the origin. So think of like L1, L2, L1. Yes.
I know that's the top one is right. If I plug in quadratics and look at LQR.
Yes.
But now it's a weird thing to think about. Like I know it's minimizing the step ahead norm.
Yeah, so it's not minimizing the step ahead norm. It's not minimizing like an explicit function of xi plus 1.
Well, no, the top one.
Yes.
That is xi plus 1.
Yes, that is xi plus 1. So I'm not solving this.
I understand, but
I'm solving this.
Even for LQR,
Yes.
that's a weird thing. That's a weird way to think.
Yeah, I wrote it this way. So people usually write this as q of xi plus 1, and then they sometimes have an end, you know, as well.
I see.
There's no difference. You can do it this way. The reason why I write it this way, because it becomes very explicit that these two terms both depend on u1. So this is, you know, you can write the LQG problem this way.
Right. No, I agree, and I see what that next line is is very nice and natural generalization. And yet I'm just trying to think like semantically, what am I looking at? What is that?
So you're saying, you see, I'm sitting at time I, and I'm trying to choose a controller that, you know, I don't want to pay too much price for the control, and I want, you know, the next state to be small. Because I cannot influence the current state, right? So what UI gets to influence is the next.
Oh, and the next state would be small if my steering is close to the negative of the disturbance.
Yes.
Okay.
Exactly. It's that is exactly. But the reason why I did this, you'll become clear in a second, is because now I can do the expectation. Because the killer for me when I had an arbitrary convex function here is I didn't know how to do this expectation. Now I do, right? I showed you this formula that whenever you have the expectation of a Bregman divergence between something deterministic and something random, you can just move in the expectation here with the appropriate, gradients of Q. Okay. So I know how to do this expectation. In particular, because Q is even, the gradient is odd, W is Gaussian, it has an even PDF, this expectation is 0. Okay. And so that is the beautiful thing. So the Bregman divergence between thing and 0 is just Q. So this became a very simple deterministic optimization, right? And it's because I changed the problem. The way I generalized the problem for an arbitrary, so I didn't do it for an arbitrary convex cost, I did it for Bregman divergence. Okay, so if my non-quadratic convex cost is Bregman divergence like this, the expectation I can do very easily. Okay, and so now for you, I just have to do this convex optimization. Okay, in the quadratic case, this Q is just the quadratic. This is exactly what happens in the quadratic.
So there were two problems, right? So one is the expectation that,
Yes.
and second is this
Yes,
optimization has a closed form.
Yes, well, I'll talk about that. That is precisely the second. So I'm going to switch the problem two ways. I did one way. I changed my problem to this, which I'm claiming that you should do. This subsumes LQG as a special case. And my claim is this is the right way to generalize LQG. This is not. That is my claim. But anyway, so then you can do the expectation. And so as Arya just mentioned, the next step is to actually do the optimization. Okay, so in principle, again, numerically, I can compute this. Let's say it's again, that's called the value function. It's the cost to go. Let's say, I numerically compute it, that's what it is. And so as before, if I'm doing the next step, I have to take this value function, add it to the cost at time t minus 1. So here's the value function, expand out xt in terms of ut minus 1. I have to do an expectation over W and then minimize. Okay? So the expectation over W for this term, I know how to do. I don't know how to do it. I'm back to where I was. Right? I don't have something close form for this. And I have to Monte Carlo this. My whole point was not having to Monte Carlo. So the only way I can do this expectation is if this M were a Bregman divergence. So if this M was the Bregman divergence between the deterministic part and the random part, I would be done. So I have to guarantee that. And so it turns out, so this is a function of this, say minus the negative of that. If you want something to be the Bregman, if you have like a function that's the difference of two things, if you want it to be a Bregman divergence between those two things, there's only one way that can be a Bregman divergence, and that is if this function is quadratic. There's no other way. And so the second thing I'm going to insist on is that the value function, the cost to go, is quadratic. I'm going to insist. Okay. So that's the second compromise I have to make. Okay. So I'm going to insist that the following holds, that there's some positive definite matrix M such that when I do this minimization over U, okay, this is my cost. This is the value function cost to go, which came from the previous time. After I minimize it, I want to get, the identical structure. Okay. This is kind of the equivalent of the algebraic Riccati equation, if anyone knows what that is. Okay. So one important thing that I should mention is this is the value function. It's not the Lyapunov function. It turns out this is the Lyapunov function that shows stability of whatever you call it. So the Lyapunov function is not quadratic. What I'm insisting has to be quadratic is the value function, is the cost of it. okay? And so here's, I don't know why this number is 0.1, but this is like the key equation. So this is what we have to solve. And so basically, if you give me a triple, a positive m, convex functions Q and R that satisfy this, we'll have an optimal stochastic Bregman divergence control. I'll show you this in a second. As I said, this is a generalization of the Riccati equation. How much time do I have? Or am I over time?
10 minutes.
Okay, I can do something. Okay, so I want to show you how to actually solve this equation. I'm going to throw a little bit more math at you. This concept of a Fenchel dual, again, I'm sure most of you have seen this. So if I have a convex function f, the Fenchel dual is what you get from solving this optimization. It's called f star of lambda, say in this case. Has lots of properties. When f is convex, the Fenchel dual is convex. The dual of the dual is f. So we're valid in calling this thing a dual. If this function is even, non-negative with minimum at 0, the dual has the same properties, even, non-negative, minimum at 0. This is an important property. If I take the gradient of f, you can view it as a mapping. If I look at the inverse of that mapping, it's the gradient of the Fenchel dual. And then finally, if I have a quadratic and I take its Fenchel dual, I'll get another quadratic where m gets inverted. So those are the properties of Fenchel duals that I will need. And so using Fenchel duals, I can actually, I'll just show you quickly, one can actually solve this 0.1 equation. So the way you do it, I'm minimizing over u. So if you take derivatives with respect to u, you get that equation. That's the optimality. Again, if you look at this equation, it's an identity in x. I'm insisting this function be equal to that for every x. So I can take derivatives with respect to x. If you do that, you get this equation. It's clear from these that I can eliminate the gradient of p. I do. And you get this equation. Very nice, simple equation. And so from this, the point is R is convex. Let's say it's strictly convex. If it's strictly convex, its gradient has an inverse. And so that is the control law. The control law is the inverse of the gradient of the cost on the control times B and A. These are the matrices from the system. M is the thing that has to satisfy that Riccati equation. It's quadratic in the cost to go. And alternatively, because the inverse of R is the gradient of the Fenchel dual, I can write it in terms of Fenchel dual. The important thing is that the solution to this Bregman divergence problem is state feedback. Only depends on the state, but it's nonlinear state. Because unless R is quadratic, this is a nonlinear. So you're getting naturally nonlinear state feedback loss. Okay, so again, I'm looking at this equation. I'll skip you the math. If you take Fenchel duals, there's a very nice way to write this. As I said, the cost to go plus Q is the Lyapunov function. And so if you take Fenchel duals, again, if people don't know any of these things, this minimization is sometimes called an infinite convolution. And so if you have an infinite convolution of two functions, their Fenchel dual is the sum of the functions. That's how this thing comes about. So the equation to solve is that the Fenchel dual of the Lyapunov plus the Fenchel dual of the cost on the control is quadratic. Let me kind of summarize what the main theorem is. Okay. So I have an LTI system driven by noise. And the claim is if I can find two non-negative convex functions Q and R and a positive M that satisfy these equations, if I can find them, then this nonlinear state feedback law solves this. It's the optimal stochastic Bregman divergence control. Okay. This is your state feedback. It's the generalization of the linear state feedback you get for LQG. This is kind of the extension of the Riccati equation. And this is the extension of LQG. Okay. So let me tell you how I'll show you a whole bunch of examples now of what this actually does. So let me just say a few things about how the theorem is used. Ideally, what I would have liked to have done is, you know, maybe I would want to put a L1 cost on the state and an L infinity cost on the, I don't know, control, and solve the problem. I cannot do that in this framework. Because I have this equation here, I can only choose one of Q or R. I cannot choose both. So for example, I can choose Q. And so the way I'll show you all these examples, I'll either choose Q, a cost on the state, then I'll find every R and M that are consistent with that through the equation, and I'll fiddle around with M until I find an R that I want. Or I do the other way around. Okay, I can choose R, and I'll show you examples of both, and I'll find an acceptable Q. So I can choose one of the two. So the framework is not perfect. I can't willy-nilly choose Q and R, but I can willy-nilly choose one of them. Okay, so Mariam asked me about certainty equivalence. So I'll just make a quick comment here. So this framework allows for separation, provided I define things correctly. So if I define, so let's say I have the system, now I don't have the state, I have observation. So I can build a Kalman filter. So the Kalman filter has an estimate of the state and the randomness that is the estimation error. So the way I change the problem now is when I'm looking at the Bregman divergence, again, the trick is to take everything that's deterministic, put it on the left, everything that's random, put it on the right, because that allows you to do the expectation. So here, what I'm putting is not AX plus BU, it's AX hat. It's the Kalman filter estimate plus the control. What I'm putting here is the uncertainty, which is the uncertainty in the disturbance, my uncertainty in the state, because I only have observations. If you do this, I can do the expectation and you get the separation. It turns out the optimal control is the same thing you got before, except the state is now the state estimate. So you'll get a nonlinear controller based on the estimate of the state. Separation. Provided, again, you define your problem to make it. So that is that. I'll wind up and just show you a bunch of examples just to show you that this stuff is for real. So I'm going to take my first example, something called elastic net. So I'm doing everything in here again for a scalar system because I can do everything in closed form. It looks, you won't have matrix equations very much. So this is the absolute value. I'm adding a tiny bit of a quadratic to it in order to make Q be strictly strictly convex. So if you choose this Q and you solve the equation that you have, R has to be like this. It has this bizarre form. If U is in this range, that's what it is. If U is out. So there's R that comes with it. M is the scalar in the quadratic for the cost to go. So I have some choice of M to kind of play around with my U, and I'll show you that. The only thing we require is that R be convex. This part of it is, this part is convex if the denominator is positive. So that puts a restriction on the M's that you can choose. And typically, if you look at this, you're trying to understand trade-offs. The bigger you make M, the more penalty you're kind of putting on your control. So you can kind of play around with M to adjust how much penalty you want to put on the control when you're trying to say sparsify the state. So let me show you some examples. Oh, by the way, this is the control law that you get. So again, if you go through the machinery, so if you look at this R, if you find its Fenchel dual and take the gradient of the Fenchel dual, this is what you so it's a piecewise linear controller in this case. Let me show you the performance of this. So it's an unstable system, 1.2. I took epsilon very small, so this is almost like an absolute value. I took m small, meaning that I'm not putting too much penalty on the control. This is the penalty on the control. This is the penalty on the state. It's almost like an absolute value. The red is the performance of the LQG controller. Again, this is the presence of noise, which is why I have many plots. I'm kind of drawing them all together. This controller, because it has an absolute value, is pushing things to zero very quickly. And it's doing that because I chose a very small m. I'm not putting too much of a penalty on the control. In fact, pushes down things to zero after one step. So it's a very aggressive controller. If I increase m, so if I start putting more penalty on the state, this slows down. It doesn't go as quickly, but still it goes quicker than the LQG. The point I want to make is, we can get these interesting control behaviors, and you can play around with m until you find one that you like. Let's look at the peak constraint case. In this case now I'm choosing the penalty on u. So I'm saying I'm not allowing any control signals that exceed t. T is the threshold, putting infinite cost after it. So you're not allowed to go beyond t. If you go through the machinery, this is the Q that comes out. Again, if you choose M is the term in the quadratic cost to go. This is what Q has to be. Again, the only thing I need for my Q is that it be convex. And if you look at this term, for it to be convex, A has to be stable, which makes sense because I have no chance of being able to stabilize an unstable system if I have a peak constraint on it. So this kind of came up. This is expected. Again, the controller looks interesting. It's another piecewise linear controller. No, the controller is not. It's piecewise.
No, but like in the second piece, it's standard.
Yeah, it's not linear. Yeah, you're right, because it's in the second piece it's flat because it cannot exceed t. Yes.
Yeah, that makes sense.
Yes. So it's saying you're linear up to some point. After that, you cannot exceed. So when you look at the state,
I always forget how these people convolutions work. So if I had it in multi-dimensional, if I had a sum of the arcs for each component, so is the Q also not being?
Yeah, so that's a lot more complex. That's why I did not do the that case. So it depends whether you're over actuated or under actuated. You can get very complicated. All of this goes through. If your B matrix is full, this stuff goes through. Once it shrinks, it becomes more complicated because you cannot simultaneously touch all the states. But I mean, it's a very good observation, kind of why I did not do it here. Okay, so again, just to show you, so I took a stable system. This is the control cost. It's infinite once we exceed 4. This is the cost on the state. Okay, so if you look at the control input, again, this is the LQG. It starts out very big here because we have a peak constraint of 4. The control, really can't compete with it. But if you look at its performance, yes, it's a bit off because it had a peak constraint, but it's not a whole lot. Even though, if you look at the beginning, how much more effort this guy put into control, we did a reasonably good job because we had a peak constraint. Think of safety control. So safety control means I'm looking at my state and I'm saying you cannot exceed T. Another convex cost. I'm not putting, that on Q. This is what the Lyapunov looks like. I was going through all the steps. That's what R star is. I don't think I need that. This is what your R will be for that Q, for the safety control. Again, depends on M. And this is what the controller looks like. So this is a controller with this particular R, whatever it means, that will guarantee that, the state does not exceed T. So this is the performance. So this was the threshold we put on the state. This is the LQG controller, violates the law. Ours doesn't. Even in the presence of noise.
For this one, we have to assume you're way over accurate, but it's still.
Not a whole lot. So if you look at the, I mean, it's whatever came out. So the controller cost is this thing. Yeah, it is kind of going up fairly rapidly.
This seems to really depend on the scale.
Yes.
So, so I know the multivariable stuff is gonna be more complicated and messy, but it's also gonna be much harder to get.
Yes. But some of them will not be. And so the way you can tell it's not is because when you solve the equation I showed, it's just like in the Riccati, right? If a solution doesn't exist, the Riccati is a quadratic equation. Whether you have a good solution or not depends on whether you get a non-negative solution. Here, when you choose, say, Q and then solve R, you can always find R. R has to be convex. If R is not convex, it means you don't have any stability guarantees. Everything will do. So you need to find it. So what you're saying is true. So for example, if I have an underactuated system, and if I put safety limits on every component of the control, I will not do this. In the scalar system, I can. If
That's kind of intrinsic to the problem.
yes, that's intrinsic to the problem. No, I don't think it is a problem. I mean, it's the point of this is that the point I want to make is I think this opens up a whole bunch of new costs that you can now deal with in the stochastic case. And the solution I would put is very elegant because it's basically nonlinear state feedback. You can, I'll show you just another crazy one, which is say this. I don't know why anyone would want to use this as the. And if you do that, then your control turns out to look logarithmic. And it turns out in this case that you can only work with a stable A. So in other words, this puts such a high penalty, it puts an exponentially high penalty on U, so that it cannot stabilize a unstable system. And this is the performance of this controller. I can do quantized controllers. So let's say you had a system that could only be up, 0, or down. Okay, that's the only controls that it could apply. Okay. Turns out you can build an optimal controller for this because we know our controller should have the form of being the gradient of the differential dual of the cost on the control. Okay, so so this function is non-increasing because it's -1, it's 0, and then it's 1. And so any function whose gradient is non-increasing is convex. So there is a convex R that corresponds to this. And from that, you can find the Q and everything. So you can set up an optimal control problem whose solution will give you only 3 values: up, 0, down. You can construct an optimal controller that does it. If you have some really dumb control device that can only do these 3 states, you can design an optimal controller. So I think I will stop here. The message I want to say basically is I think this is the right way to extend LQG because it subsumes it as a special case. There were 2 things I needed to do. I had to bring in Bregman divergence. I had to put the random stuff on the right, the deterministic stuff on the left, so I can do the expectation. And then I need the cost to go to be quadratic. The second one is what restricts me from willy-nilly choosing Q1. I can choose 1. I can enter.
Okay, but let's thank Babak.